thing that says like predicting products, the thing that's stapled together, the activity series and solubility rules. So this is like a little picture of a woodcut with you know, a bunch of early chemists or uh, people who do alchemy, where you're trying to make new chemicals of some kind. And for the longest time, we've understood that you could take certain natural materials and mix them together, and a chemical reaction will form, and you get new chemicals. And so you need to get good at predicting whether or not chemical reactions take place, and if they're going to be single replacement, double replacement, um, or if any synthesis takes place, if a decomposition will happen, and under what circumstances. We're going to start with the single replacement reactions because they're actually kind of the easiest to understand. So in a list of different types of reactions, they're not necessarily the first one. Um, we use the activity series, that's activity series chart, to help predict whether or not reactions will take place. And the way that that activity series chart works is if you look on the chart, it just has a list of elements, and that list of elements is not like in order on the periodic table. It's not you know, alphabetical. It's not by formula mass, but it's by the how reactive the individual metals are. And the arrow in the slide isn't as complete as the activity series that's on the paper, but in that activity series, the things that are at the top are the most active or the most reactive metal. Lithium, which is in the upper left-hand corner of the periodic table, right underneath hydrogen, is incredibly reactive. Um, Lithium metal, you have to store it in oil. Like, you got to have a container with oil, and the lithium's got to be in the oil. Because if lithium touches air, it reacts with the oxygen in the air. If lithium gets wet, it explodes violently. So lithium metal has to be like immersed in oil just to have it in existence on its own. And then all the way at the bottom is gold. Gold is incredibly non-reactive. Gold is incredibly stable. It's valuable in jewelry. Like, you can find a piece of gold jewelry that was made like forever ago, and it doesn't tarnish. It doesn't react with anything. It's very, very stable. It's very difficult to make gold react with anything. The only way you can get gold to react, and it's really not necessarily a reaction, but you can take gold atoms and turn them into gold ions if you put them in aqua regia, which is a very, very, very strong acid solution. Otherwise, gold is very, very stable. So the activity series goes from gold at the bottom, which is basically incredibly non-reactive, all the way up to, like, if you touch lithium metal with your bare hands, it will react with your hand. It will violently burn your skin. Your skin will go away. You can't hold it. Like, you put a piece of lithium in the palm of your hand, it will burn through your hand and come out the bottom. That's not good. Gold doesn't do that. Otherwise, you'd be like, propose marriage to someone, be like, I'm going to put this gold ring on your finger, and it'll slice their finger off. Gold works exactly opposite. So how this activity series relates to predicting whether or not reactions take place is you look at the position of the metals relative to each other, and if a metal is above another metal, it's more reactive and will replace a metal in a compound. And it's the same thing with, on the activity series chart on paper, it also has a list of nonmetals: fluorine, chlorine, bromine, and iodine. And it turns out that when you look on the periodic table, that's actually in order on the halogens. So, like, the periodic table on the side of the room, fluorine, element number 9, fluorine is on top, then chlorine, bromine, and iodine. So the order of reactivity is somewhat predictable on the periodic table. Your thing doesn't look that good, but basically, like, calcium would replace magnesium, magnesium would replace zinc, zinc would replace nickel, nickel would replace copper. You know, any kind of order, you can make metals replace each other in a reaction, in a, like, a single replacement reaction. The The most active are at the top, the least active are at the bottom. So it doesn't matter if it's the metals, the metal chart, or the non-metal chart. All right. So what you do in a single replacement reaction is it's always that there's one chemical that's like trying to replace some other kind of chemical. And generically in a single replacement reaction, you have this idea that you've looked to like basically identify them so far, but you have like chemical A plus chemical BX makes, chemical B by itself, and then A goes with X. So in other words, this single element that's by itself replaces an element that's bonded to another atom or an ion group or something. So this atom replaces that one, and this one ends up going on its own. Whether or not that takes place depends on whether chemical A or chemical B is higher up on the activity series. So if chemical A is higher on the activity series than chemical B, then the reaction proceeds. It actually happens. If instead chemical A is below chemical B, then no reaction takes place. It just doesn't happen. So if you happen to know what the activity series is in order, like memorized, but you don't have to memorize it, you can know off the top of your head whether or not the reaction will even occur. So a more active element will replace a less active element in an ionic compound. If otherwise, no reaction. Let me just give you a real basic example. And it has to do with this idea that when we draw the reaction, it goes in the forward direction. So if you look on the activity series, if I write this reaction, K plus, let's say, Al, I don't want to use aluminum. That's kind of a pain. I'll just do strontium, strontium hydroxide or something. Potassium and strontium hydroxide form a compound, be potassium hydroxide plus strontium. And this reaction occurs because when you look on the activity series, potassium is higher up. Potassium is high on the chart and strontium is lower. And because potassium is higher on the chart than strontium, the potassium will replace strontium, potassium goes with the hydroxide, and the strontium stays by itself. But another way to read a chemical reaction is when we write these reactions where you've got like chemical A plus BX changes into B plus AX, the reverse reaction doesn't take place. Once you form those products, it's done. It's over with. You finished it. It's like when you take the iron and the oxygen, burning the steel wool, you got the 9-volt battery, you touch the steel wool, the iron and the oxygen makes iron oxide. You've made your products and you're done. Taking that back to make oxygen and iron is really tough. So most reactions are non-reversible. So you can also predict here that once you made these products, potassium hydroxide and strontium, those two things don't react to form the reactants because strontium is below the potassium on the ion chart or on the activity series in the first place. So whether or not the reaction takes place has everything to do with which one is above the other one on the activity series. Okay, so here's some other examples. This is examples that are right in the stapled together slide thing. So these are possible reactions that could happen. And all we want to do is determine, will the reaction take place or will the reaction not take place? So what you got to do is look and see for this element here, Na, that's sodium. Where is sodium on the chart? So sodium is like right here. And what sodium would replace is calcium. And how you know sodium would replace the calcium, you can know it a couple different ways. First off, calcium is also on the chart, but chlorine is not. There's no chlorine on this activity series. So if sodium is going to replace something in the calcium or the chloride, it's going to be the calcium. So we got sodium, we've also got calcium. Sodium is the metal that's all by itself. So if sodium is going to replace calcium to make like sodium chloride, that only happens if sodium is above calcium. And it's not. So no reaction takes place. The idea is like if Na is above calcium, then a reaction, we actually just like write Rx or Rxn, will take place. And here the sodium is below the calcium on the activity series, so there's no reaction. What people write a lot of times is NR, no reaction. It's kind of like, oh, if you're doing a problem with like in trig or calc or maybe even algebra 2, and there's a problem about limits and the limit doesn't exist, you might write like limit does not exist. You just write DNE, like it just doesn't happen. You know, it's like not a thing. Or like, you know, you're trying to find like the slope of a vertical line, and you know a vertical line on a graph has no slope. It's undefined. You don't write a value and you don't say what the slope is. You just say doesn't happen. Same deal here. So if sodium's above calcium, the reaction happens. This one, it does not. So the next one, we've got tin. SN is the symbol for tin. So tin's down here, and tin would replace nickel. So nickel's right there. And if tin, which is the element that's by itself, is above nickel, then the reaction will take place. And here it's not. The tin is below the nickel. So there's also no reaction. No reaction happens. Because the tin, SN, is below the nickel. And it really doesn't matter the order you write the reaction. For instance, if I write it like this, SN plus Ni SO4, oh, there doesn't need to, well, this should actually be, it depends on if there's one or two. It doesn't matter here. If I write it in this order, it doesn't make a difference either. It doesn't matter for the reactants which reactant comes first. So it's not the order of the reactants. What matters is if the element that's by itself would replace a similar element that's already in the compound. This is the same thing, also no reaction. So it's not the order in which the elements appear in the reaction the way it's written, because it's sort of irrelevant whether the tin is written first or the nickel's written first. What matters is that the element that's by itself has to be above the element that's trying to replace in the activity series. I didn't put the other one on. Hold on, I need to copy something else. Let me find my other little activity series. Is it this one? Nope. Here it is. I'm going to put this on here. Okay, so the next one, this MgBr2 plus Cl2, the element that's by itself is chlorine. Now, chlorine does not appear on the metal list. Chlorine is a gas. And the criteria is to look to see what chlorine would replace. And chlorine, because it's on the list with the gases on the right-hand side of the activity series, the chlorine wouldn't replace the magnesium. The chlorine would replace the bromine. Chlorine and bromine are on the same activity series list. So you got bromine and you got chlorine. This element chlorine is by itself, and chlorine is above bromine on the activity series. So because the chlorine is above the bromine, this reaction will happen. So if you react magnesium bromide and chlorine, then what you end up with is magnesium chloride and bromine. And both bromine and magnesium, or both bromine and chlorine, are diatomics. So you got to have like the 2 after the bromine, and it's already balanced. But in this case, the chlorine, it's above the bromine. So because the single element is above the element that's in the compound, the reaction happens. Similarly, once you make magnesium chloride and you try to react it with bromine, nothing happens. And that's because the bromine is below the chlorine, so it's a one-way reaction. The products form the compound, or the reactants form the products, and the products are stuck like that. All right, so then iron hydroxide and lead. So you look to see where lead is. Lead is right down here. I'll just put a box around it. And then lead would replace the iron. Iron is up here. So because the lead is below the iron, there's also no reaction that takes place. Lead is below the iron, no reaction. So if you have a solution of lead hydroxide, or a solution of iron hydroxide, and you throw a piece of lead in, the lead just stays lead. Nothing happens. So the reactions that I set up for you to do yesterday, those are really rigged so that they take place. When you put zinc into the copper chloride, because the zinc, like the one reaction you did yesterday, you took zinc plus copper chloride, CuCl2, and that reaction proceeded. You should have seen that the zinc got like really dark, like almost turned black, and the copper chloride solution, which was initially, maybe it was copper sulfate, copper chloride, doesn't really matter. That solution was initially blue, and this colored solution should have got like lighter and lighter and lighter, and maybe even turned colorless. Because the zinc is above copper, zinc is right here, and copper is right here. Because the zinc was above the copper, that reaction took place because the elemental zinc by itself is above the copper on the activity series. If instead you were to put a piece of copper into zinc chloride, nothing happens. Because copper is below zinc, if you put copper into a solution of zinc something, nothing. It just gets wet. You take it out, shake it off, and it's the same copper you had to start off. The deal why the zinc looks like it turns black is because you're actually coating the zinc with copper atoms, and copper atoms in bulk look, shiny like a penny, like look at that copper color. But when it's a very, very fine coating, it looks more like black. All right, so you want to use that activity series to help you out. You got this other paper, the one that says predicting products of a single displacement reaction or a single replacement reaction. So here's the idea. This is what we're going to work on and try. So in a single replacement reaction, generically, you've got some kind of an element that's by itself, element, in this case, like element A, and it reacts with some kind of compound with, elements like BC, or it could be element B and polyatomic ion C, and A would replace B, making B plus AC, and that happens if A is above B on the activity series. It can also be true for nonmetals. In the case of two gases, gas C and gas D, they can switch place, but only if the element that's by itself is above the other one on the table. So we're going to check the activity series to see any kind of reactions that don't happen. For any reaction that occurs, we're going to either swap the metal or the nonmetal, and then look at the charges to figure out what the formula is going to be. And we have to remember the 7 diatomic elements using that mnemonic Brinkelhoff, or hydrogen, and nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So if any elements are going to end up appearing by themselves, and if they're diatomic, we got to make sure to write the formula with the 2 after it. All right, so, that arrow didn't show up. It doesn't really matter. Okay, so you got this one reaction, CaF2 plus Cl2. And a reaction might happen, and if it does, we want to write what the products are going to be. So the element that's by itself in this reaction is chlorine. So the best thing to do is start off by looking to see which element appears by itself in the reaction. Chlorine appears by itself. Chlorine is right over here. And what is chlorine going to replace? It's going to replace something else in that same column. So chlorine is in the same column with fluorine, bromine, and iodine. So chlorine could replace the fluorine. You got calcium fluoride and chlorine. And it could be that calcium replaces the fluorine. So whether or not the calcium can replace the fluorine depends upon their relative position. In this case, the calcium, which is the element that's by itself, is below fluorine. The calcium does not replace, or the chlorine does not replace the fluorine. No reaction takes place. And that's because this single element, it's not part of a compound, is below the fluorine, below the similar element that appears in the compound. If it were like calcium chloride and fluorine, then the reaction would take place because fluorine is above chlorine on the activity series. So in that case, there's no reaction. All right, in number 2, so you got lithium. That's the element that's by itself. Start off with whatever thing is by itself. Try to find that on the activity series. So you got good news. Lithium's above everything. Basically, lithium reacting with any kind of metal, the reaction is going to take place. So that lithium's by itself. We got lithium at the top of the table. We're pretty sure already it's going to do a replacement with something. The element that's similar to lithium is magnesium. Magnesium is right here. So because the element that's by itself, so the single element, it's above the magnesium, we know that the replacement will take place. So instead of lithium being alone with magnesium chloride, the magnesium is going to go by itself and the lithium will go with the chlorine. So how does the formula end up looking? Well, on the periodic table, lithium is in the first column. So you know that if you're going to make a compound with lithium and chlorine, you got lithium with a charge of +1, and then chlorine on the periodic table is in the 17th column, so that's Cl1-. So lithium, when it goes together with chlorine, because lithium would have a charge of +1 and chlorine has a charge of -1, that compound is just LiCl. There's not going to be a 2 after it or anything. But because lithium has a charge of 1, chlorine has a charge of 1, it's just LiCl. And then the magnesium goes by itself, like LiCl plus Mg. So the replacement of lithium for magnesium happens because lithium is above magnesium on the table. And there's something else we can do. That equation's not balanced. Because magnesium had a charge of 2 and it was MgCl2, this is an unbalanced equation. And you now know how to balance equations. So because there was 2 chlorines on the left, it looks like there's only 1 chlorine on the right, you got to put a 2, you got to put a 2 in front of that lithium. And by putting 2 in front of lithium chloride, you're going to need a 2 in front of the lithium on the left-hand side too. All right. I mean, like in chemistry, things don't go away. There are no topics that have disappeared in this course. Being able to write chemical equations, that is a skill that you use throughout the entire course. The idea that we need to have the law of conservation of mass followed and have to balance the equation, that will go on through the course. Now, the thing we'll do next week is look to see that lithium chloride, is that going to be a solid or is that going to be aqueous? And there's a way to tell, but for now, we don't really know the states of anything. But, well, it turns out you can tell that magnesium chloride is going to be aqueous. The lithium chloride, it's tough to know, but I'll show you how to tell. It's that solubility chart. All right, then number 3, here's the element that's by itself, zinc. It's all by itself. You find zinc. So here's zinc. And then look to see, well, what could it replace? The other thing that's in that column is sodium. Na is sodium. Because zinc is below the sodium, no reaction takes place. That's because zinc is below sodium on the activity series. So that's how it goes. Now, you got this big John, there's 20 of them. So the paper that says like chemistry, single displacement reaction worksheet, you kind of need to have a periodic table handy so you can tell what charges are going to be. You got the activity series, which you use to determine whether or not the reaction takes place. And then if the reaction takes place, you ought to write the products correctly and get the equation balanced. So I'll do a couple with you here, then you got to practice this. So in the first one, the element that's all by itself, Ag, that's silver. Silver is pretty darn low. We make jewelry out of silver as well because it's very non-reactive. But you might know silver can tarnish, like kind of turn like, kind of get like a black kind of coating. It tarnishes slowly, but reacts. It doesn't react as, it reacts better than gold. I mean, you'll never see gold with tarnish on it. Gold's just beautiful. So you got gold, and what else is on this or you got silver. What else is on this column is potassium. Potassium's way up here. So because the silver, which is by itself, is well below the potassium, there's no reaction. The Ag is below potassium. But then when you compare zinc and silver, zinc is up here, and then silver was far below it. So because the zinc is above silver, then you can predict how the product is going to go. Now, zinc is a transition metal. It's in that D block in the middle of the periodic table. So you want to have like your ion chart. Let me see. I can copy the ion chart into the folder for this week too to help you out. Let me see where that's going to be. That was like somewhere around Christmas time. (14/7). Here it is. Yeah, I guess we didn't include zinc. Yeah, I guess we didn't include zinc on the ion chart, but so you might have to look it up. But zinc is Zn2 plus. So whenever this compound forms, the zinc is going to replace the silver. So it ends up to be zinc. Well, I'll write it over here. Zinc is Zn2 plus, and then nitrate is NO3 1 minus. So if the zinc is going to replace the silver, zinc is going to go with the nitrate. Zinc has a charge of 2 plus, nitrate has a charge of 1 minus. So, you know, the two different methods are whatever the charge for the zinc is how many nitrates you need. Whatever the number of nitrates is, that's how many zincs you need. So the compound is going to be ZnNO3 2. So one of the products is zinc nitrate, NO3 2. And because the silver goes by itself, it's just Ag. So you got zinc and silver nitrate makes zinc nitrate and silver. And this equation is not balanced because there were two nitrates on the right, but there's only one nitrate on the left. So you need a 2 in front of the silver on both sides. So it's zinc plus 2 silver nitrates makes zinc nitrate and 2 silvers. All right. Hydrogen is a kind of a funny element. Hydrogen is in the upper left-hand corner of the periodic table. It has the same electron configuration as everything else in group 1 on the periodic table, but it's a gas. And it only needs 2 valence electrons instead of 8, like everything else. But in terms of its chemical reactivity, you consider it to be a metal. So although it's a gas, on this activity chart, you'll find hydrogen right here. So the thing that aluminum could replace is hydrogen. So the two things in number 3, you got hydrogen, and you got aluminum that's up here. Aluminum is above hydrogen. So because aluminum is above hydrogen, the reaction happens. And what you end up with is you've got aluminum, and aluminum is on the third column, or is in column 13 on the periodic table, has a charge of 3 plus. And then sulfate, SO4, has a charge of 2 minus. So when aluminum replaces hydrogen, the aluminum goes with the sulfate anion. And aluminum had a charge of 3, sulfate had a charge of 2. So that chemical formula is going to be Al2 SO4 3. Because the aluminum's got to go with the sulfate. The aluminum had a charge of 3, sulfate has a charge of 2, so Al2SO4. And then the other chemical that has to be formed is because aluminum replaces hydrogen, hydrogen's got to go all by itself, and hydrogen is a diatomic, just H2. So you got the aluminum sulfate and the hydrogen. Those are the two products. This is not balanced. I'm going to need a 3 in front of the hydrogen sulfate, and then we put a 2 in front of the aluminum and a 3 in front of the hydrogen. And that ends up to be balanced. So you got 2 aluminums on each side, 6 hydrogens on each side, and 3 sulfates on each side. Or you can look at it as 3 sulfurs and 12 oxygens. Turns out that H2SO4, you might recognize that as sulfuric acid. Any compound where hydrogen is the cation is an acid in solution. So when it's hydrogen something, it's an acid. And most metals react with acids, with the exception of copper, silver, mercury, and gold. So any compound or any metal above hydrogen on the activity series, this is really like all acids have hydrogen as the cation. So basically, if you put any of these metals that are up here on the activity series into an acid solution, you're going to get a chemical reaction. But if you put mercury, gold, silver, and copper into most acids, you get no reaction. It just chills like that. So like you should keep metals, like little bits of metal and stuff, away from kids. But like if a little kid swallows like a piece of metal, it reacts with the acid in their stomach and changes into solution. It's not really a big deal. Like if there's a little piece of iron and a kid swallows it, and you're like, we got to rush them to the doctor. Oh no, they swallowed some metal. By the time you get to the doctor, that iron is already reacted with the acid in the stomach, and there's no iron. There's iron ions, so But iron is a good nutritional supplement. If you have anemia, you're good. You know, you can't really OD on iron. I wouldn't try to though. That's kind of weird. All the other things up there, like you can take zinc supplements, and there's like powdered zinc in the tablet. You swallow that, it hits your stomach. The zinc metal changes to zinc in solution. It actually turns out, you might know that we fortify diet with different kinds of things. We generally, when you want to try to fortify people's diet so you get a good diet, you can sneak things into different food. So we intentionally put extra vitamin D in milk. We put iodine in salt. We put iron in cereal. If you take, we'll do this, maybe we'll do it later on in the course. If you take like any kind of breakfast cereal that says fortified with iron, especially like one that works really well is uh, Total Raisin Bran, and you like grind it up, they actually put iron filings directly in the food. And you can take a magnet and pull the iron filings out of Total cereal. So we straight up dump powdered iron metal into the food. You don't really taste it, and it's fine enough it doesn't damage your teeth or anything, but you end up like swallowing the iron. And the iron hits your stomach, the solid iron changes to iron ions, and the iron ions get absorbed and go into your blood because it's iron in hemoglobin that allows oxygen to be carried around in your body. Every hemoglobin complex has a molecule called heme, and the center of heme is an iron. It, uh, Transporting oxygen and carbon dioxide around in your body is done by iron and iron only. So people who are anemic, who have low iron or low blood iron, they have the heme molecule, but it's missing the iron in the middle, and they're unable to carry as much oxygen and carbon dioxide. That's the condition of anemia. Some people have difficulty keeping enough iron in their blood, so you take like iron supplements. Historically, if you like cook with a cast iron frying pan and use a metal spatula, as you do that, you wear the pan down a little bit. You get a little bit more metal in the food, and you consume the iron from the cast iron frying pan, which sounds kind of weird, but you don't have to go around eating iron, but you just kind of naturally get some in your diet. All right, so you can try the rest of those. We'll work on those tomorrow too, and go over the rest of them. So keep on practicing that. Hold on, I got to switch to this thing. New share Safari. No.